In this video, I'm going to discuss concepts about sensitivity analysis for linear programming problems. I'll also talk about how to read the sensitivity report generated by Excel solver. However, we will not focus on the methodology that is used to obtain the information in the sensitivity report. Instead, what we would like to focus on is how we interpret the report and how the information in the report may help in the scenarios where the estimates of the coefficients or parameters are not accurate. Let's start with the question about what is sensitivity analysis. Sensitivity analysis is used to determine how the optimal solution is affected by changes in the objective function coefficients or the right-hand side values of the constraints. Why is it important to do the sensitivity analysis? It is mainly because that sometimes we will not be able to estimate the coefficients that are relevant to the problem accurately. Sensitivity analysis allows us to answer some what-if questions about the problem. Let's take a look at some examples. In these optimization problems, we want to maximize the value of 5x1 plus 7x2, subject to the constraint listed in the slide. We can first draw the boundaries of the constraints and find out the feasible region for the solutions. Then, we can draw a line that has the same slope as the objective function. Because this is a maximization problem, we can move the objective function line upward until we reach the less feasible solution to find out the optimal solution for x1 and x2. Next, suppose that we increase x1's objective function coefficient from 5 to 9. What will happen? We can draw a line that has the same slope as the new objective function, and then we move the new line upwards. After we reach the optimal solution of the original objective function, we see that there are still other feasible solutions that can give us higher objective function values. So, we can continue to move the new objective function line until we reach the best solution. In this example, we see that the base solution changes from 5 and 3 to 6 and 2 when we change x1's objective function coefficient from 5 to 9. Therefore, if we are using an inaccurate value of x1's objective function coefficient, and the possible value of this coefficient can be as large as 9, then it is possible that the solution we find in the original formulation is not the best solution. So, what is sensitivity analysis? Sensitivity analysis wants to answer the question about whether the optimal solution is sensitive to the parameters used in the objective function or the constraints. We want to know how much inaccuracy in the parameters is allowed. We want to evaluate the robustness of the solution without exhausting all possible values of parameters. Next, we solve this linear programming problem using Excel solver. By choosing sensitivity report after we solve the problem, we will get the sensitivity report in a separate spreadsheet. Now, let's see how we can interpret the sensitivity report. We see that there are two tables in the sensitivity report. The first table's title is variable cells, and the second table's title is constraints. We can also see that the optimal solution for the linear programming problem is x1 equal to 5 and x2 equal to 3, which is shown in the third column of the first table. The objective function coefficients that are used to solve the linear programming is in the fifth column of the table. Then the last two columns of the first table will allow us to answer the question about what is the largest amount of increase or decrease in each objective function coefficient, such that the optimal solution will remain the same. The columns that says allowable increase gives the largest amount of increase in the corresponding objective function coefficient, such that the optimal solution shown in the table is the best solution if all the other parameters remain unchanged. The column that says allowable decrease gives the largest amount of decrease in the corresponding objective function coefficient, such that the optimal solution shown in this table is the best solution, given that all the other parameters remain unchanged. In other words, if all parameters remain unchanged in the linear programming model, except for x1's objective function coefficient, then phi and 3 is the optimal solution so long as x1's coefficient is within the range between the lowest bound phi minus 0.3333 and the upper bound of phi plus 2. So, the range of optimality for x1's objective function coefficient is between 4.6667 and 7. In other words, if x1's objective function coefficient is increased by more than 2 or decreased by more than 0.333, then the optimal solution for x1 and x2 will no longer be phi and 3. Similarly, we see that the allowable increase for x2's objective function is 0.5 and the allowable decrease for x2's objective function is 2. So, the range of optimality for x2's objective function coefficient is between phi minus 2 and phi plus 0.5 if all other parameters remain unchanged. So long as the x2's objective function coefficient is within the range, the optimal solution for x1 and x2 will still be phi and 3. In other words, if x2's objective function coefficient is increased by more than 0.5 or decreased by more than 2, then the optimal solution for x1 and x2 will no longer be phi and 3. The second type of questions we want to ask in the sensitivity analysis is about how a change in the right-hand side for a constraint might affect the feasible region or perhaps cause a change in the optimal solution. We will use a term called shadow price. Shadow price is the improvement in the value of the optimal solution per unit increase in the right-hand side of the constraint. The sensitivity analysis for the right-hand side values is available in the second table in the sensitivity report. Let's take a look at the sensitivity report for the same example. In the second table of the sensitivity report, we see that the third column is the left-hand side values of the constraint and the optimal solution. For example, constraint number 1 is x1 less than or equal to 6. The optimal solution is phi and 3 for x1 and x2. So constraint number 1's left-hand side values and the optimal solution is 5. Similarly, constraint number 2's left-hand side value and the optimal solution is 2 times 5 plus 3 times 3, which is equal to 19. Constraint number 3's left-hand side value and the optimal solution is 5 plus 3, which equals to 8. The fifth column of the table gives the information about the value of each constraint's right-hand side. The fourth column gives the shadow price for each constraint. The shadow price is the change in the optimal objective function value per unit increase in the right-hand side of a constraint. For example, we see that the final value of constraint number 1's left-hand side is 5, which is less than its right-hand side value of 6. Let's think of the right-hand side value of constraint number 1 as the amount of available resources that are related to constraint number 1. Therefore, if constraint number 1's left-hand side value at the optimal solution is less than the right-hand side value, then we can think of this as if we do not exhaust all the resources that is related to the first constraint. Intuitively speaking, this means that we have leftover resources for this constraint. Therefore, even if we further increase the availability of this resource by 1 unit, the extra resource will not help us improve our objective function value. After all, we have already had excess resources. That's why we see that the shadow price is 0 for the first constraint's right-hand side. Next, we notice that constraint number 2's final value of the left-hand side is the same as its right-hand side value. Intuitively speaking, this means that we have used up all the resources that are related to the second constraint. And we said that constraint number 2 is binding. Because we use up all the resources that are related to the second constraint, it is possible that we can improve the objective function value if we can relax the constraint by increasing the resources available to us. The shadow price of the second constraint is 2. This tells us that if we are able to increase the right-hand side value of constraint number 2 by 1 unit, then we will be able to find a solution that can improve the optimal objective function value by 2. Suppose the objective is to maximize the profit, and we interpret shadow price in monetary value, then the shadow price for constraint number 2 means that if we are able to get 1 additional unit of the resource for this constraint, then the maximum worth of that 1 unit resource is $2. Similarly, constraint number 3 is binding because the final value of its left-hand side is the same as its right-hand side. All available resource for constraint number 3 has been used, and it will make sense to check if increasing the resource can lead to a better outcome. The shadow price is 1 for constraint number 3. This means that if we can increase the right-hand side value of constraint number 3 by 1 unit, then we will be able to increase the optimal objective function value by 1. So a natural question to ask at this point would be, why do we care about the shadow price? Think about the following scenario. When we have limited budget to improve the performance of our decision, we want to spend the money smartly, efficiently, and effectively. So we would like to know how we can spend the money to achieve the largest improvement. In many linear programming problems, each constraint is a limitation for a type of resource. And shadow price can tell us how much improvement we can gain from adding each type of resource. At this point, you may ask a question about the shadow price for the non-negativity constraints. The shadow price for each decision variable's non-negativity constraint is shown in the reduced cost column in the first table. And we can see that the reduced cost corresponds to x1, non-negativity constraint is 0. This is intuitive because the optimal solution for x1 is 5, which is already higher than 1. So, if we increase the right-hand side of x1 non-negativity constraint from 0 to 1, the objective function value will not change. Similarly, if we increase the right-hand side of the non-negativity constraint of x2 from 0 to 1, then the objective function value will not change, and therefore the reduced cost associated with this constraint is 0. Now, I want to talk about the last 2 columns in Table 2. The last 2 columns that says allowable increment and allowable decrement given that information about how much the right-hand side of the constraint can change without changing the shadow price. Let's first look at the allowable increase of constraint number 1's right-hand side. The value 1e plus 30 means 10 to the power of 30. Just think of this as a very large number on infinity. The super large amount of allowable increase in constraint number 1's right-hand side value is intuitive because constraint number 1 is not binding. There are already leftover resources and the shadow price is 0. Since we already have excess resources for constraint number 1, additional resources will not improve the solution even if we continuously increase the amount of resources available. That's why the allowable increase for constraint number 1's right-hand side is infinity. When we look at the allowable decrease of constraint number 1's right-hand side, we see that the allowable decrease is 1. This means that if we decrease the right-hand side by more than 1 unit, then the shadow price of 0 will not be applicable. Similarly, the allowable increase and allowable decrease for the rest of the constraint give the feasible range such that the corresponding shadow price remains the same. Finally, let's revisit the investment example that we see in the solver tutorial and apply what we just discussed to interpret the result from the sensitivity report. In this problem, we are considering 5 stocks and bonds, and we want to determine the best portfolio to maximize the projected return. The decision variables are the amount to invest in these 5 stocks and bonds, and there are constraints about total budget and the amount that can be invested in these stocks and bonds. We formulate the problem as a linear program and solve it in Excel solver. By choosing the sensitivity report options in the last step, we will be able to obtain the sensitivity report. Now, let's try to answer some questions using the sensitivity report generated by Excel solver. Will the optimal portfolio change if real cost annual return is decreased to 0.09? We see that the decision variable corresponds to real cost is x5, and the objective function coefficient for x5 is its annual return. If the annual return changes from 0.104 to 0.09, then the rate is decreased by 0.104 minus 0.09, and it is equal to 0.014. This is still within an allowable decrease of 0.016. Therefore, the optimal solution will not change. Next, let's check how will the optimal projected profit change if we can increase the right-hand side of constraint number 5 by 1000. Constraint number 5 is a total budget constraint, and the shadow price for constraint number 5 is 0.104, and the allowable increase is infinity. Therefore, if we increase the right-hand side of constraint number 5 by 1000, then we can expect the profit to increase by 0.104 times 1000, which is equal to $104. And this is intuitive. When we increase the total investment budget, the optimal projected profit will increase as well. Let's see one more example. Will the optimal projected profit change if constraint number 1's right-hand side increased by $100? Constraint number 1 is the minimum amount to invest in City of Miami bonds. The shadow price for constraint number 1 is minus 0.051. Therefore, if we increase the right-hand side of constraint number 1 by $100, then we can expect the profit to decrease by 0.051 times 100, which is equal to $5.1. This is intuitive. If we take a look at the annual return for these 5 stocks and bonds, the City of Miami bonds have the lowest annual return rate, and therefore, if the decision maker is forced to invest more in the City of Miami bonds, then his projected return will be lower.